Okay, we can start. So good morning to everybody. Good morning. The objective of this seminar is to train and do research in response to the energy transition faced by the EU, the Mediterranean and the sub-Saharan region in Africa, and the need to mitigate the effects of climate change. In view of this target, it is critical to work and do with universities and other institutions to enhance offerings in theoretical and technical training in the region for renewable energies and energy efficiency. This seminar is organized by Civis, Amenet, ECRI, and CERMI. Civis is made up of Aix-Marseille University, University of Athens, University of Bucharest, Université Libre de Bruxelles, University Autónoma of Madrid, Sapienza University of Rome, Stockholm University, and the University of Tübingen. Amenet is the African, Mediterranean, and Europe Jean Monnet Nergot, funded by the European Union. ECRI is the ECOWAS Center for Renewable Energy and Energy Efficiency, and CERMI is the Center for Renewable Energies and Industrial Maintenance of Cape Verde. Experts who are delivering the lectures of this workshop are working in outstanding international research groups and energy companies. Today, we are starting with a first intervention, which is in charge of Dr. Sovet Karbuz, Director of the Mediterranean Observatory for Energy. Dr. Karbuz, I pass you the floor. Thank you. Are you there, Dr. Karbuz?
You have to unmute yourself.
Sorry, I didn't unmute myself. Thank you very much for this introduction, and thank you for the kind invitation, Professor Mela. And I will, in the next hour, try to explain first what OME does briefly, and then I will present you the main conclusions of a book that we just published, called Mediterranean Energy Perspectives to 2050. Let me first share my slides, and then do you see the slides? Can you see the slides?
Yes.
Okay, very good. So just a few words briefly about OME. We are a private non-profit association. It is an association of leading energy companies operating in the Mediterranean region. We are basically working as a think tank of these leading companies and partners and some associate members, some of the logos you see below the slide. And we also serve as the Secretariat of the Union for the Mediterranean Gas Platform. As you know, Union for the Mediterranean is headquartered in Barcelona, and we had the privilege of visiting beautiful city, Barcelona, several times. So what this Union for the Mediterranean does, I will come to in a few minutes, but just about OME, how we work, because OME is the only industry association in the Mediterranean region that brings not only oil, gas companies, but also electricity and companies that are focusing on renewable energy and also electricity and gas transmission. So we have over 30 years experience, and we carry out mostly some strategic studies for our members. So unfortunately, most of them are not available to public. And we also regularly conduct training activities for the junior or middle management of the companies in our member area. So now come back to Union for the Mediterranean Gas Platform. I don't know whether you are aware that 5 years ago, the energy ministers in the Mediterranean region, and all the countries in the Mediterranean region agreed to create 3 platforms, one on electricity and the other one on renewables and energy efficiency, and the third one is on gas. So the aim of all these energy platforms is to increase cooperation between the countries in the northern and southern shore of the Mediterranean. And for the UFM gas platform, the aim is to increase regional structured dialogue on gas matters. So the energy minister of the countries of the Mediterranean had a meeting in July, and they agreed to further enhance the cooperation and increase especially the capacity building activities, just for your information. And we conduct several conferences and capacity building activities and workshops, but this is normally open to the ministry people, either Minister of Energy or national companies, or the people from Ministry of Foreign Affairs. So in other words, the people who participate to our workshops are normally designated by the country's energy ministry or Ministry of Foreign Affairs. So I had a few promotional videos to show, but I'm kind of scared that I might not lose the connection. So that is why I would like to skip. But when you go to UFM website, you will have more information about these issues. So for specifically UFM gas platform, we have a website, dedicated website, and we have English, French, and Arabic versions are available in the website, and there are member areas. In these member areas, we show several reports. So with the agreement with the European Commission and Union for the Mediterranean, we are trying to make some of the studies public, hopefully within this year. Having said that, the studies that we are thinking of making public is, for example, the one that we finished in September on renewable gases in the Mediterranean region. The other one is power to gas applications in the Mediterranean region. Another one is methane emissions in the Mediterranean region. Of course, everything we do covers the Mediterranean region, even though it gives overall global developments, but then focuses where available by country developments, but the focus is on Mediterranean region. And we had a report finished in July, August on reducing carbon intensities in urban areas in the Mediterranean. So there are several. So together with the Commission and UFM Secretariat, we will find out what to make public so that general public also benefits from the studies we conducted so far. Now, coming back to OME, as I said, we conduct several studies, but most of them are not available to public, only to our members. What is available is public is this publication, Mediterranean Energy Perspectives, that we started to conduct since 2008, what we do is that, as you may know, World Energy Outlook, when you look at the annexes of the World Energy Outlook, you see supply-demand balance by fuel, by sector, to 2040 or 2050, nowadays 2050. And we produce more or less the same thing, but country by country in the Mediterranean region. So within the OME, over the several years, well, 13 years now, for every single country in the Mediterranean, we develop an in-house model, energy supply demand model, and then perform some forecasts to 2050. Before we were doing 2040, but now we extended 2050. And in the meantime, we created two special reports. One is Egypt's energy future, and the other one is Turkey's energy future. Turkey is one of the largest energy consumer in the Mediterranean, and Egypt is not only largest but also an important oil and gas exporter in the region. So we just published a new version of this Mediterranean Energy Perspectives to the horizon 2050. So we covered 26 countries in this book, but we, as I mentioned before, we showed the results in regional basis. So total Mediterranean, North Mediterranean, South Mediterranean, even though we have country by country results. So of course, we had this COVID. COVID has changed a lot of things in 2020. In fact, this publication was almost ready in 2020, but we waited several months to introduce the impact, short, mid, or long-term impact of COVID on economy and on energy sector. We usually perform two scenarios. One is the reference scenario, or you may call it business as usual scenario, and the other is more environmental friendly and more energy transition scenario. But in this publication, together with the European Commission and Union for the Mediterranean, we developed a ProMed scenario, which is in fact a kind of near zero carbon for the horizon 2050 in the Mediterranean region. So before showing you some general results, because it is very detailed study, it is impossible to explain it in 1 hour. But I would like to give you some overall important messages. As I mentioned, we model 26 countries. I say the countries, but just I have to mention here that we lump 5 countries together: Albania, Bosnia, Macedonia, Montenegro, and Serbia. We model as one single country. For all the other countries that you see, what is defined as Mediterranean, which is in line with the Union for the Mediterranean definition of the Mediterranean. So as you see, Jordan, for example, doesn't have access to Mediterranean. I mean, it doesn't have a coast, but it is considered Mediterranean. Similarly, Mauritania. So this is as presented by the Union for the Mediterranean. Now, some basic facts. Maybe you already know. In the Mediterranean region, there are 550 million people. These 550 million people represent 7% of the world's population. The energy demand in the Mediterranean region is 1,000 million ton oil equivalent. Again, this is almost 7% of the world's energy demand. CO2 emissions of the Mediterranean is equivalent to 6% of the world's CO2 emissions. And when we look at the economy, the Mediterranean region's economy represents 7% of the world economic output. As you can see, in fact, the Mediterranean region, from population, from economy, to energy and CO2, represents more or less 7% of the world. This is a key number to always keep in mind. So just a little bit about the modeling. So we use, in fact, the same modeling approach that is used by the International Energy Agency, because including myself, several of the team in OME were working at the International Energy Agency, and some of us were working on the world energy outlook. So we basically, in terms of methodology, we use the same methodology, and even the software that we use are the same. But as you know, World Energy Outlook does not, or International Energy Agency does not model the countries separately. It models only very large countries like United States or Europe or China, India, some countries individually, all the rest are lumped together. Now, it is a bottom-up model, so we are looking sector by sector, and for every sector, to each sector, and then also by field. So the main determinants of the equations of the forecast is the population, economic growth, or per capita income, and energy prices. For the Mediterranean region, especially for the South Mediterranean countries, energy prices are not very significant in equations, partly because, as you are aware, the fact that in many countries the energy prices are subsidized by the government. So this subsidy, of course, make it insensitive to prices or the demand to adjust according to prices. Now, COVID had a large impact in the Mediterranean region. It represented 9% of slowdown in the economy. And interestingly, most of the largest impact was north because of the industrial situation, as you can estimate. Now let's look at the main assumptions that I mentioned: population and economic growth to the future, because they will be important factors determining the energy consumption in the region. So between 2020 and 2050, in other words, in the next 30 years, 128 million more people will be living in the Mediterranean region. So this is over, but in fact, all of this growth will come from South Mediterranean countries. In the North Mediterranean, in contrast, the population will decrease by 13 million. So all the demographic growth in the Mediterranean region to 2050 will emanate from the South Mediterranean region. And similarly, when we look into the future, the share of economic growth in total Mediterranean region will change throughout time. So today, North Mediterranean represents the largest share in total Mediterranean economic activities. But when we go to the future, we will see that more than half of the economic growth in total Mediterranean region will be accounted in South Mediterranean. So South Mediterranean, in terms of population and economy, will be more and more important in the next 30 years. Of course, that will have big impact on economic growth and energy demand. Sorry. So, but before I want to show you the results. I mentioned before that we have three alternative scenarios for the evolution of energy demand in the future. So you don't need to note anything because you will be receiving the slides. One is the reference scenario. We can also call it the business as usual scenario. But here the important thing to underline is that this business as usual scenario, in fact, incorporates the nationally determined contributions or NDCs by the countries submitted to the United Nations. So we assume that there will not be international financing. So these are, in other words, unconditional nationally determined contributions. So for the EU countries, so we mostly rely on the targets country by country from the European Commission, and in the south we looked at their national situation, strategies, and their submissions. So this is the reference scenario. So it is kind of business as usual, but takes into account of unconditional NDC to the future. Now, the second scenario is proactive scenario. This is similar to other one, reference scenario, but in this one, we assume that the international financing will be readily available. As you know, when you look at the country submissions, their targets with or without international financing are quite different. So the targets with international financing is more ambitious. And we also assume that in this scenario, there will be more strong implementations of energy efficiency measures. And we also assume that the renewable targets that are envisaged by the countries in their NDC submissions will be satisfied. Now, again, just a summary, we have a business as usual kind of NDC without financing. Now here we have NDC with financing, with strong implementation of renewable targets and energy efficiency. Now, we have another scenario, so-called PROMED scenario. This scenario is developed by the European Commission, as OME, as the Secretariat of the UFM Gas Platform, and some or several, in fact, leading experts from the region, because to set the assumptions, we had several workshops, and we established a group of advisors, which include some energy commissioners of the EU. So in this scenario, we assume that it is kind of Euro-Mediterranean or Mediterranean Green Deal for zero carbon scenario can be reached. But of course, as you know, for the EU, net zero, the target is 2050. But we cannot take 2050 for every single country in the Mediterranean because they have different targets. That is why we assume that for most of the countries, because it depends from country to country, for most of the countries, this net zero target is 2060. So again, country by country it varies, but the aim is here to achieve as much possible the net zero between 2050 2060. Now, I will show you now the results for energy demand and CO2 emissions by fuel by looking at these three scenarios. So in the business as usual scenario, Mediterranean as a whole, we forecast that energy demand in the region will increase nearly 40% between 2020 and 2050. So we are expecting, under current scenarios, around 40% increase. But if we achieve the NDC with international financing plus the aggressive implementation of energy efficiency plans and push for renewables, in 2050, in fact, this increase could be reduced 26%, or let's say a quarter for 2050. If you go a little bit further, if you assume that net zero, if you have the net zero target, in fact, in 2050, the discrepancy between business as usual scenario and PROMET scenario would be 40%. This is a very, very big difference. Will that be easy? Of course, it will not be easy, but I will show you later on what kind of benefits it would bring. Now, when we look at the Mediterranean, sometimes the results may not look too aggressive or too interesting. But when we separate North Mediterranean and South Mediterranean, then things become more interesting. When you look at the left side of the chart, where I show North Mediterranean under three scenarios compared to 2018, we see that in every single scenario, whatever we do, from net zero or even business as usual, the energy demand in the North Mediterranean is expected to decline over the next 30 years. But when we move to the right, in the South Mediterranean region, even in the PROMET scenario, the energy demand in the region will increase. But the degree of, or the intensity of this increase will depend whether we are in PROMET, which is 18%, or business as usual, which is nearly double compared to today. So when we look at the Mediterranean again as a whole, the main focus should be in fact in the south. Now, what does that mean for the CO2 emissions? Now, in the business as usual scenario, we calculate that CO2 emissions could increase 28% between 2020 or 2019, because it differs. For some countries, we have base year 2019, sometimes 2020. So it may increase 28%, or when we look at the other scenarios, proactive scenario shows that the CO2 emissions could decline 39%, or in PROMET scenario, that means net zero, In net zero, the CO2 emissions could decline almost 74%. This is a big lesson to keep in mind. But of course, it is sometimes very easy to talk about overall energy demand. But when we look at the different parts or different energy types, we will see a different issue. When we look at the oil, we see that in every scenario, oil demand in the Mediterranean region will go down. So this is clear. Despite the population will increase, the economy grows, but the people will be using less and less oil because they will be switching to other alternative sources. In gas, even in gas, the total gas demand in the region will decline, but here there is an important thing. Here we will not be talking only about natural gas in the future. We will also have green gases. What are these? Green gases is biogas, biomethane, and hydrogen gas. So these three together combined, we call it green gas. Well, I don't know, maybe we could have found a better term, or methane alone. I don't know. In the world, nobody agrees at the moment common terminology how to call it. I mean, natural and unnatural gas under one single term. So the importance of these green gases will increase. Of course, in some countries, the green gases will be much more important. When you look at, for example, the Total has published last week or 2 weeks ago, if I'm not wrong, an energy outlook. They show that in the world level, the share of these green gases will be 1/3 of total gas demand in the future. The other 1/3 will be natural gas, and the other 1/3 will be kind of gas with carbon capture. Anyway, now coal demand, as you could imagine, will go down in the Mediterranean region, wherever you look, in the south and in the north. So this will have an important factor, but again, I would like to underline that green gas will account for 20% of total gas demand in the Mediterranean region in the year 2050 in the PROMED scenario. That was the demand side. Now let's look at the production, because as you know, there are some important fossil fuel producers in the Mediterranean region. Either coal, like Turkey, is an important, in fact, lignite producer, or oil and gas, like Egypt, Algeria, and Libya, or even Israel. So when we look at this, the future evolution. So this is, I don't want to show you country by country evolution. So the fossil fuel production, but it is mainly because of, in fact, natural gas production. The natural gas production will peak in the Mediterranean region in the first half of 2040s. After that, it will start to decline. So it will bring all the other oil and gas together, because oil production will remain nearly stagnant, and you see that coal production will go down slightly, but overall there will be a peak fossil fuel production in the Mediterranean region in the first half of 2040s. Now, I mentioned this gas. Gas production will peak around 2042. Why it is 42? Well, it showed up, came up like that because we estimate country by country production, and then we sum all this production, and it showed 2042, and then we see a sharp decline. Sharp decline because, especially this is because of Egypt, because in Egypt, many of the fields are in deep offshore Mediterranean, and the decline rates in deep offshore fields are very high. So that's why we will see a sharp decline. Whereas in oil, we will have a slight increase and then stable. In fact, oil production will decline basically everywhere in the Mediterranean, except for Libya. So the slight increase that you see here is because of Libya, because we assume that, of course, the security situation and the political situation in Libya in the midterm will change, and Libya will become a large oil producer as it was before. So just a summary for fossil fuels, but with a focus on oil and gas, I showed you that fossil fuel production will in fact decrease after early 2040s, but demand will also, well, depending on the country, of course, but in a regional, demand will also decline sharply when we approach to 2050. What does that mean? Is that here you see net oil and gas trade in the region. So the dark blue ones are the North Mediterranean, and this pink or red, I don't know how you see in your screen, is the South Mediterranean. So let's look at the first one for oil. In 2018, North Mediterranean countries were in fact net oil importers. In the south, there is a slight net exporter. In reference scenario, both Mediterranean regions, I mean South and North Mediterranean, will become a net oil importer. In proactive scenario, South Mediterranean will be self-sufficient, but again, North Mediterranean will be net importer. But when we come to PROMET scenario, because of the huge decline in demand, even though the production is going down, because of a huge decline in demand, the North Mediterranean will become a rather small net importer, but the countries in the south, as a region, will be or may become a net exporter. We see a similar picture also on the right for natural gas. We see that in the PROMET scenario only, the South Mediterranean region can become, in fact, large gas exporter. And as a Mediterranean region as a whole, even the region could become a net gas exporter. But in the proactive and reference scenario, the Mediterranean region as a whole is again net importer. So these are important things. Now, let me first move the share of renewables in energy mix. So here, with renewables, the share I show you in terms of energy demand, share of renewables in electricity generation, and share of renewables in total final energy consumption. When we look at the energy demand, in 2018, renewables accounted for 12% of the total energy demand in the Mediterranean region. So when we move to 2050, this share will increase. But when you look 2050 PM, that means PROMET scenario, I mean in net zero scenario, the share of renewables is nearly 50%. So this is huge. When we move to electricity generation, we see the huge increase to 2050 among the scenarios from 26% in 2018 to as high as 71% in PROMET scenario. In total final consumption, you don't see this huge jump because this is total final consumption. It's only this end user sectors, meaning industry, buildings, and transport. This excludes the power generation sector. So as you can see, the huge impact of renewable or the increasing share of renewables in both energy mix and electricity generation mix in the PROMET scenario. Now, when we look at the electricity demand, this chart may be tricky because it includes several aspects that I want to show you one by one. Every bar here shows electricity demand in the Mediterranean region. So the light yellow one is the north, dark one is south. So together is total Mediterranean region. You see that under reference scenario, total electricity demand in the Mediterranean region will increase 78%. Whereas in the PROMET scenario, we could have an increase of 65%. Again, this is for 2050, between 2018 and 2050. And we have the shares of renewables in electricity generation. So in 2018, the renewables had a 28% share in total electricity generation, but this share could increase, as I showed you before, up to 72% in PROMET scenario. All right, now what does that mean? If you move to PROMET scenario, I showed you before that Mediterranean region could become, depending on the fuel, the net exporter, and it could turn from net importer to net exporter, plus we are using more and more renewables, and we reduce the share of fossil fuels in electricity generation. It has direct impact on the energy dependence of the region. By region, of course, by the country. When we look at the Mediterranean region as a whole, 39% of the energy in the Mediterranean was, or 39% of the energy consumed in the Mediterranean region was coming from foreign sources. In business as usual scenario, this will increase a little bit in terms of percentage. 40% of the energy used in the Mediterranean region would be imported from foreign sources. But in PROMET scenario, on the contrary, the Mediterranean region could export 15% of its energy demand to outside. This is because of the South Mediterranean, because South Mediterranean region could become an important oil and gas exporter in PROMED region. Whereas when you look at in the north, the chart in the middle, the dependence, North Mediterranean will continue to be dependent on imports, energy imports, even in PROMED scenario, but the magnitude of this dependence will decrease from 59% in 2018 up to 10% in PROMED scenario in 2050. Okay, what does that mean? Just I'm coming nearly to the end. What does that mean for CO2 and the distribution of CO2 emissions among technologies? As I said, the CO2 emissions will increase under reference scenario. It is normal, but we could reduce CO2 emissions in the region radically in PROMED scenario. And when we look at the distribution or the shares of several parts, we see that the most important contribution of reducing CO2 emissions, in fact, will come from energy efficiency. That will be followed by renewables. That will be followed by carbon capture and utilization and storage. And finally, green gases. As I said, this could be biogas, biomethane, and hydrogen. So in fact, we do not expect hydrogen development in the region too much by the year 2050 because of several reasons. We just published a paper. You can look at OME website, the EU's hydrogen import potential and where this hydrogen can come from. We look at several Mediterranean countries with some cost estimates. So we think that contrary to maybe the EU, it is better for the South Mediterranean countries to produce hydrogen and inject the hydrogen into natural gas grid instead of trying to find application which is technology intensive and it comes with a lot of cost is to use it for transport or for the buildings. These are not yet very mature technologies, and we don't think that it will be really mature in the South in the next 30 years. So let me conclude with some main messages. One is the current policies followed by the countries in the Mediterranean region is not enough to satisfy its demand and reduce CO2 emissions at the same time. That things have to be changed. It is not only the issue is not the only climate change, but the energy dependence and energy security will become more and more important in the future, as important maybe as climate change. And for this reason, especially the countries in the South need to try to adjust their energy policies accordingly if they want to gain both from reducing the CO2 emissions, increasing the employment, and continue to become net energy exporter status. That especially we see in oil and gas. Oil and gas production will stagnate in the future been, in fact, decline in most of countries except for Libya, and gas production will sharply decline after it reaches its peak in the early 2040s. So, in fact, energy transition would turn the Mediterranean into a net oil and gas exporter by 2050. Like the European Green Deal, in fact, there is another key message. We may need, in fact, a Euro-Mediterranean Green Deal. So this cannot be done by a few countries. This requires a large cooperation, and that what we think is that this Union for the Mediterranean could play an important role increasing cooperation and the awareness in that regard. Another very important key issue is the energy efficiency, and renewables will be the cornerstone of decarbonization in the future in the region. We don't want to separate, or put one technology in front of the others. No, we think that all technologies and policies will be needed for this energy transition and effectively and efficiently reduce the CO2 emissions. So these are basically the messages that I would like to give. And I show here the link where you can have the executive summary in a text format. And I will be happy for any questions you may have.
Okay. Thank you very much, Dr. Cavus, for your interesting intervention. Not only interesting, but very well empirically based. So the time for questions, yes, for opening the questions, I would want to make you a question. Achieving this carbon neutrality for the Mediterranean region in 2050 or 2060 wouldn't only involve a significant acceleration of deployment of clean energy technology, yes, but also require wide behavioral changes in some sectors like mobility, buildings, and industry infrastructure in order for implementing drastic energy efficiency measures. Efficiency is a key point in this discussion. So, would you mind explaining and commenting a bit more these relevant issues, since they are quite challenging? Thanks.
Yes, I think very, very good summary. Actually, you mentioned. Perhaps energy efficiency will come before renewables, because as we know, especially the South Mediterranean region is endowed with large potential for both solar and wind energy. So that is not the issue. The issue is that what needed, especially in the South, is the cultural change in the way the people consume energy. What do I mean with the cultural change? I give you an example in Turkey, from Turkey. Turkey is a net energy importer, and energy costs are basically for electricity and gas is subsidized. But instead of saving the energy in winter, for example, today, as you know, you witness the same situation in Spain. Electricity and gas prices are increasing, and we are approaching the winter. So it will be perhaps, as the forecast, if the forecast become true, we will have a very cold winter. But what the people do, they don't want to lose anything from comfort. If the apartment is very hot, what they do, they open the window. Instead of reducing the thermometers. So This is a cultural change. Or if you, in Turkey, for example, I've seen, I think a few times, we have it in Spain, in France too. You go to a restaurant, okay? Outside there are the heating, either by electricity or gas for smokers. I'm a smoker too, but I mean, why the government, why you and me, we are subsidizing the cost of heating smokers that are outside? This is insane. And then we are complaining about high prices and the burden of this importing fossil fuels. But then we are free to lavishly waste this energy. So, it is not energy consumption. We are in fact wasting the energy. So this is okay. We can have a better application that use less energy. I understand this is energy efficiency, but more and more important, we need to change the culture, the way we consume energy. That means we need to learn energy conservation. We need to use less energy. That is it. If you don't need the electricity, we should simply switch it off. The government does not have to subsidize me because I want everywhere 100-watt ampoules. This doesn't make sense. And unfortunately, this is especially the case in the South Mediterranean region. Look, when you go to Cairo, the first thing you realize in summer, in any hotel, in any government building, whenever I went, that happened to me, you will be freezing. You will be freezing. It is subsidized, but they keep it cold. They keep it cold, and they all open the windows to get the warm air inside. But we are freezing this, cooling the space, and you are opening the window. No, I mean this doesn't work like that. So that is why subsidies sometimes really is the key. You should reduce the subsidies, and the people should understand the costs, what it means. So that is why, yes, energy efficiency is important, but energy conservation is also very important, especially again for the countries in the south, but not only, even for the north, for the developed countries. We should be adapting.
Okay, thank you very much for your interesting answer. So, any other question, please?
Yes, I have a question. I don't know if you can hear me well.
Yes.
Yes.
Yes. Okay. First of all, thank you very much for your great presentation. It was very, very interesting. I have a question, which is it possible to have some explanation on the model that you use to have the forecast and all the interesting results that you have here? Yeah. Is there a place where we can have this information? Thank you.
Well, in the book, we explain the methodology, but unfortunately, we are selling the book. But I can discuss it maybe to make a copy available for you so that you see it. So these are the model is the bottom-up model. We look at the sector by sector energy consumption, and for every single sector, for every single fuel, we have an equation. So this equation is solved by econometric models. And it is a bottom-up econometric model, in fact. For every single sector, for example, assume total energy demand in steel industry. So we have coal consumption in steel industry is a function of steel production, the amount of coal used per ton of steel production, and future capacity, etc., increases for simulation. And then we estimate the elasticity for coal consumption in steel industry, electricity consumption in steel industry, etc. and then we aggregate them. So we look how well it can represent the past development in terms of elasticities. And when we look at the future, from steel industry, again, we have to look at for every single country, how many tons of steel production capacity will come online, how many tons of steel production capacity will retire in the future, what will be the steel production efficiency in the future, etc. So these are used to make the simulation into the future. So basically, it works like this. Of course, throughout the way, we do several assumptions. As I said, as I mentioned, we assume that when the countries put their renewable ambitions in NDCs, in the model, we assume that those targets will be achieved. So in other words, we are fixing some certain dates, some targets. So we assume that we will reach, this could be in a fast way or in a smooth way. So basically, first econometrics and then simulation.
Okay, thank you very much for your answer. And if it's possible to get the book, of course, we are very happy to have it.
Hopefully, I will get in touch first with Professor Mella or we'll find it out.
We are sending the book for you. Don't worry about it. Right away, we send it. Okay. So thank you very much for your really interesting intervention, Dr. Carbos, and keep in touch. We need to go to the next topic. So again, thank you. We appreciate.
I thank you very much. Again, I have to be out because I have doctor coming now, and we'll see. I thank you very much, and have a good day to all of you. Bye-bye.
Thank you. Have a good day. Bye.
Bye-bye.
So we continue with the next topic. The next topic is going to be explained by Luis Arribas. Luis Arribas is currently researcher at the Research Center for Energy, Environment and Technology. And Luis Arribas has been involved in renewable energy systems for more than 25 years, both in solar and wind systems. Thank you very much, Luis, for being here, and I pass you the floor.
Okay, thank you, Jose, and good morning, everyone. And thank you also for the previous speaker, because he was at the hospital, so it's very valuable. So I will give a brief introduction to wind energy in this session, and I will try to start sharing my screen. So can you see my presentation now?
Yes, we can.
Yes, we can.
Okay, so as Jose said during the introduction, I work in CEMAT. CEMAT is a public research center in Spain, which is devoted to energy in general. And in particular, I work in the renewable energy division, and more particular in the wind energy unit. So my plan for this session is to give a start with some comments on the wind energy, some milestones, some applications description. Then we will address some concepts related with the wind energy technology, the different components that form a wind turbine, and some classifications according to different criteria. We will also cover some issues related with wind resource, which in this particular renewable energy technology is quite important. And the last point we will see is the state of the wind energy worldwide, and also for the future, the challenges for the future. So some milestones in recent, well, more or less recent history, because this American windmill, which is very famous everywhere, also because it appears in some Western films, and it's relatively recent because it was first built in half 18th century. So even though wind energy started several millenniums ago, we could say that this is the first turbine, more or less, from our era. It was built, as I said, some centuries ago, for the first one, but it still there are manufacturers both in America but also in Europe, and if I'm not wrong, even in Africa there are some that are building nowadays this American windmill. It's mechanical, and it was mainly used for pumping applications. The great milestones in our history, in our era, we could say that it's the use of wind energy for electricity generation. It started at the end of the 19th century, and curiously, because at that time there was no internet, or the communications were not so easy as they are nowadays, but more or less it started at the same time in two different distant places. Bruce produced his wind turbine in the US, in America, and Paul Lacour produced his idea of wind turbine in Denmark, here in Europe. So, of course, that nowadays these designs look very, very old-fashioned, and that you can see also that they are quite different ideas. One on the Bruce design was based more on the American windmill, and the Lacour design was based more on the European mills. But even though designs didn't are not maintained nowadays, and even though they were quite different, both of them were the two first ones to produce electricity from wind energy. Perhaps the other milestone that changed these designs into what we know nowadays as the modern wind turbines are the airfoils. The airfoils were used in the aeronautic industry, but not in the wind energy industry. So at the beginning of the 20th century, some scientists started to study the possibility to apply these airfoils coming from aeronautic industry into the wind turbines, and they did, and that's how they shaped somehow the design of wind turbine, modern wind turbine that we know nowadays. The pictures on the lower part of the slide, you can see on the left a large blade which is being manufactured. You can see the size of the blade compared to the size of one person. And on the right lower part of the slide, you can see what is really an airfoil. An airfoil is like a cross section of the blade. So when you cut the blade, you get a shape which has some particularities we will see now, and that's what is called an airfoil. So following with this introduction, if we talk about the typical applications of wind generation, we should start with the grid-connected application, which nowadays is related to distributed generation. Historically, as we have seen, it was the last one to come, the grid-connected application, but nowadays is the most common. Nearly everywhere in the world, it's not difficult to find some large-scale wind farms. They are called wind farms when they are installed on site on the ground. And in the past, there were only these wind farms, but nowadays we also have wind farms on the sea. And in this case, they are usually called offshore wind farms. The application in the sea, the offshore wind farms, look much more challenging from the technical point of view, but also bring some advantages in relation to the on-site wind farms, onshore wind farms. As for example, the wind resource may be much higher, much more stable. There are no obstacles. There are no mountains. There is no orographies. But of course, there are some challenges, as I mentioned, such as working such as an environment, as harsh environment as the sea, and also that in some places the depth of the sea is quite large. So these applications have started in those places, like in the North Sea in Europe, where the depth of the sea is not that high. So if the large-scale grid-connected applications are very famous everywhere, maybe it's not so famous the application of medium and small-scale grid-connected wind turbines. This is more related to what is called distributed generation, and it may be applied at the domestic level, maybe a small wind turbine connected to the grid in our own home, or at an industrial or commercial level, where the not so small, but even much smaller than the large-scale wind turbines, medium scale, we could say, wind turbine is connected, for example, in an industrial area or commercial area. The second set of applications is that related with water. Of course, it's not only for wind, because most generating technologies have applications related with water, but wind is one of them, also has this kind of applications. We already saw the pumping applications of the American windmill. There are other designs for pumping applications with wind energy, which are not only mechanical like this one. We can also find electrical pumping applications using wind energy. Water desalination is another application for producing fresh water supplied with wind energy. And nowadays it's becoming very outstanding also the application related with hydrogen. It's not new, because in the past there were already some projects related with hydrogen production using wind generation. But nowadays that you surely know that hydrogen is being proposed as a key actor in this energy transition. And of course, the production, as it was mentioned in the previous presentation, the production of hydrogen is sought with clean energies. And the cleaner production of hydrogen is using renewable energies, which is called green hydrogen. Among the different renewable energies that can produce hydrogen in large amounts, of course, wind energy is one of them. It's not the only one, but it's one of them. And in this sense, nowadays there are many activities related with large-scale electrolyzers supplied with both solar and wind energy. The use of this hydrogen is not only for electricity generation, but mainly for other sectors. That's why hydrogen is such important, because it's one of the only vectors, energy vectors, that can connect more or less easily with most of the sectors. And the third set of applications is the isolated ones. These were the first ones, and it's the kind of application where renewable energies have always been attractive, because in these applications, energy is usually much more expensive. And so now renewable energies are quite competitive, but in some decades ago, they were not so competitive related with conventional energies. And since then, they have been applied in this type of application, mainly for rural electrification. I will classify the isolated applications in two groups: the small power groups, which I will call hybrids. This the main feature of this group of application, isolated application, is that they are based on some electrochemical storage, usually a battery. The battery defines somehow the working principle of this system, and you can see that I call them hybrids because usually they will be composed of different generating technologies. In this case, there are wind and solar PV generation. There may be also a diesel generator, but the component that is needed to define this configuration is the battery as a storage system. Traditionally, this configuration has been used for smaller size systems, usually less than 50 kilowatts. But nowadays, everything's changing in relation with renewable generation. And nowadays, we can find configurations such as this, which are much larger, even from megawatt size. In the past, the megawatt size was covered with this other configuration, which I will call wind diesel. It's also hybrid because we have wind diesel, and we may also have wind solar PV diesel. But the difference is that here we don't have a large storage component. We don't have a battery, and if we have a battery, it's not large in comparison with the daily load. This has been the typical configuration for islands, smaller islands, not so small. For example, in the area where this training course is related, I know that some of the islands in Cape Verde have used this type of configuration of wind diesel. It may be, in fact, nowadays we can find solar PV diesel, only solar PV diesel, because of the cost decline in solar PV generation. So I will focus mainly on grid-connected applications, as they are the most famous, but unless I will specify in a different way. But of course, when we talk about rural electrification, this set of configuration of isolated applications are key for the rural electrification. And one comment, which is more or less philosophical, which is the relations between isolated and grid-connected applications. Nowadays, I would say that they are merging more and more, and the isolated applications are becoming more grid-connected, and the grid-connected applications are becoming more isolated, in the sense that the grid connection is reaching some renewable energy percentages, penetration levels that are bringing the same issues, the same difficulties that the isolated systems have. So my vision is that in a short time, all these worlds will be joined, and really the solutions for isolated will not be much different from the distributed generation solutions. Okay, that was in relation to the introduction. Now we will move to the next block, which is related to technology. And we'll start with some basic concepts related with wind energy. This is perhaps the starting point, which is the power that wind takes when it moves. This expression brings some information, important information, when using wind energy. We can see that it's multiplications of 4 factors. One of them is a constant, 1/2. The other 3 ones are 3 variables, which are the air density, the rotor area, and the wind speed. But you can see that the wind speed is cubed. So from these factors, of course, the factor that is more important in the sense that it influences more to the power in the wind is precisely the wind speed, because a variation of doubling the wind speed means that the power is multiplied by 8. So this is not common for every renewable technologies. So the influence of the wind resource characterization is paramount for the wind generation. Well, you're on the picture on the right, you have, if you're not familiar with this nomenclature, the rotor is the collection of the blades and the hub. The nacelle is the room where all the other components are placed on the top of the supporting structure, which is usually the tower. So the wind speed is the paramount variable in relation with wind energy. And we also have 2 other variables that are important. One is the area, the rotor area, the area of the surface that the blades cover when they rotate. That's the rotor area. And of course, this is the only variable that will depend on the design of the wind turbine, because the other 2, the air density and the wind speed, will depend on the site where the wind turbine is placed. And the other variable, which is the air density, depends on different meteorological parameters, but is defined principally by the altitude of the site. The higher the altitude of our site, the lower the air density. So air density is maximum at sea level and is minimum in the Everest, for example. Perhaps one doubt arises when one hears this, because we all have seen that there are wind farms installed in high mountains or in the mountains. Of course, in the mountains, the air density is lower, but we have to take into account that the wind speed may be much higher. And as the wind speed influence is much more important than the air density influence, then there is not only a compensation, but an increase in the final output production. So that's the power that the wind takes. When the wind field meets the rotor extracts a part of that power, but it cannot extract it all. There is a physical limit, which is, it was discovered or described by the German scientist called Albert Beth, which he mathematically showed that there was a physical limit, that it was not possible to extract more or less 60% of the wind power. I mean, from the energy that the wind takes, the rotor as a maximum could only extract 60%, nearly 60%. This percentage, or this efficiency, this part that the rotor is able to extract from the wind, the power in the wind, is called power coefficient, and is placed. You can see here in this equation how the equation describing the power in the wind is multiplied by the power coefficient to obtain the power extracted by the rotor. The power extracted by the rotor is still a mechanical power, a rotational mechanical power, which we will with which we will produce the electrical output power, for which we need to include also the efficiencies of the components. Usually there will be some mechanical adaptation, some conversion into a electrical generator, we will see now in the components, and also some electronic matching in order to connect to the final application. So with these three equations, we can see that how from the power in the wind, we get the power output from our wind turbine. So following with these basic concepts, some words about the airfoil. The airfoil is really a special design to take advantage of the lift force that is produced by the wind. When the wind meets any object, it produces a resultant force, which is called here F. But this resultant force can be decomposed into components. The drag force, which is in the same direction as the wind, and in our case, the most important one, which is the lift force, which is precisely in 90 degrees in relation with the direction of the wind. Usually, in most objects, the drag force, the drag component is larger than the lift component. But if we want to use the lift component, we can modify the shape of our object. And if we produce a shape like the one that is the picture in this slide, which is called the airfoil, then we can see how the lift component is much larger than the drag component. That's the main idea and the behind the design of airfoils. This is more or less the same, but with some of the nomenclature that is commonly used in relation with airfoils, just in case you could take a look at some of literature, existing literature, so you can understand what is they are talking about. We can see how the drag component is in the same directions as the wind speed, which in this scale is called U sub infinite, and the lift component is perpendicular to this drag component. As a composition of both components, we get the resultant aerodynamic force. From this diagram, it's I would like to highlight this variable, which is called the angle of attack. The angle of attack is the angle, which is here it's called alpha, is the angle between the wind direction and the main direction of our airfoil. And this angle is important because it's an angle we can use to regulate our production. In general, of course, this angle of attack will be selected, will be chosen in order to maximize our production. As you can see on the graph on the right, there is a maximum for the relation, which maximizes the relation between lift and drag, which is in this case is nearly at zero angle of attack, is 0 degrees. Really, it's not zero. It's some degrees, but it's close to zero. It's maybe 3-4 degrees. So usually the blades are fixed for that angle in order to maximize production. But we can also use this angle of attack by varying this angle of attack. When we want to regulate the production, we can move the blade to the diminishing the efficiency of the extraction of energy in the rotor. This is used very commonly nowadays in most of wind turbines, as we will see now. Going to the most important characteristic curve, this is the main one, which is called the power curve. And in this power curve, the output power of the wind turbine is represented against the wind speed. We can distinguish three different working zones. On the left, the zone where there's no generation, the wind speed is not high enough to produce electricity, maybe high enough to make the rotor turn, but in order to produce electricity, the rotor needs to turn, of course, but apart from start rotating, it needs to reach a minimum rotational speed. If not, there will be no electricity production. Once this starts to happen at the starting wind speed, there is an area where the control or the strategy or the algorithm of the control of the wind turbine tries to extract as much as power as possible. It is the maximum power extraction zone. In this area, in this zone, the wind turbine tries to follow the wind, the incident wind speed as much as it can. But there is a time, there is a wind speed where the wind turbine stops following the wind speed, and we start the regulation zone. This happens for every wind turbine. The wind turbine is designed for a specific nominal power, and from that nominal power on, it starts regulating. Otherwise, the wind turbine should be prepared to work at very, very high wind speed. So the sizing of the components would be huge. Of course, the wind turbine has to stand any wind speed, but in order to optimize the size of the generator, the size of the blades, and the size of each component, it is limited to the nominal power. So we distinguish three different zones: no generation, maximum power extraction, and regulation zone. This power curve is the main curve in order to identify any wind turbine, independent from the type of wind turbine. And there is another, which is not so common to be available, but well, just to let you know that there is a curve which is called the CP lambda, or the power coefficient versus tip speed ratio, which is more related to the aerodynamics of the rotor. And the great advantage of this curve is that only with one curve, the whole family of working points of the rotor are represented. Yes, just to let you know, I will not go much into detail about this, but just to let you know. Okay, so here we have the components of a wind turbine, and from these components we can understand how a wind turbine works. this such as it is depicted here, the wind flow would come from the left. The first thing that the wind flow meets is the hub, and then the rotor. In this case, the rotor is cross-sectioned, but you can imagine that there would be a blade going upwards and another blade going downwards, and another. Usually, there will be three blades. The third one would be in the corresponding position. So, as the wind flow meets the rotor, because of the design of the airfoils of the blades, it would start to rotate. As the rotational speed increases, it will. You can see that it's mechanically coupled to this set of components, mechanical components, which are the main bearing, the main shaft, the gearbox, and the generator. So, due to this mechanical coupling, when the rotor starts rotating, it starts moving, rotating also the generator, which is the one that produces electricity. Why do we need this mechanical coupling? Because
Do you have any trouble, Luis?
Luis, can you hear us? You have been silenced. Luis.
Okay. Can you hear me
Yes,
now?
now it's okay.
Okay.
Yeah, now it's okay. Yeah.
Okay, go ahead.
I don't know. I was muted because I didn't change anything. So I don't know if you hear what I was explaining about the components, or do I start from the beginning here?
Yes, yes, we have heard it. It's okay.
Okay.
Yeah.
Okay.
Yeah.
Okay. Thank you. So this mechanical coupling between the rotor and the generator is necessary to adapt the rotational speed. The rotor rotates usually from the aerodynamics needs. It rotates at several RPMs, where the generator, due to the electrical needs, usually rotates at several hundred RPMs. So in order to adapt these two different axes rotating at different speeds, we might need what it's called a gearbox. Gearbox is like a transformer for RPMs. We could say it simply that way. Okay, so once the rotor plus generator set reaches the rotational speed able to produce electricity, so the electricity production starts, it may still need some adaptation to be connected to the end user application, but we would be producing electricity. Other components we have here, in this case, we have a wind direction sensor. This sensor is the one that rules the yaw mechanism. The yaw mechanism is the one that places the whole nacelle plus rotor opposite to the wind flow. So with the information from this sensor, it's taken to the yaw algorithm, which is the one that decides when to move and how much to move the whole collection of which is in the upper part of the tower. I mean, the rotor plus the nacelle. There are some safety elements like the brakes for the whole drivetrain, and also the brake for the yaw mechanism. And more or less, this is how a wind turbine works and how these different components appear in these working principles. Not all the existing wind turbines respond exactly to these components because there are different designs, but they all respond to the same working principle. Okay, so we move on to the classification of wind turbines, and according to the size, we will see different criteria. According to the size, we can distinguish between large, small, and mid-size. I'm not sure. Okay, yeah. Well, this figure has some years because the size for the large wind turbines is growing more and more. Nowadays, perhaps you know that there are some wind turbines larger than 10 megawatts that are being built. So the size of the large sector, the large range, is much higher, but the medium smaller wind turbines ranges is not much different nowadays. Mainly for the small wind turbines, the range is up to 100 kilowatts. We could distinguish between this range for the commercial wind turbines, which is the range for larger, small wind turbines, up to 100 from 20 up to 100 kilowatts, and the residential sector, which is for the lowest size wind turbines, less than 20 kilowatts. I will not say much about the difference between small and large, but they are quite different, even though they both are wind turbines. But the wind resource with they work, the costs of the installations, and the characteristics of each one of those families are quite different. And also the costs, the producing costs, the LCOEs. In this graph, you can see the yellow points, the yellow dots correspond to large wind turbines, and the LCOE is quite low, and nowadays we could say it's even lower. And the capacity factor, we will see now what is the capacity factor, is much larger. So, of course, the difference is that the small wind turbine bring very valuable energy in the places where they are installed, but we cannot see them as equivalent. I mean, we cannot think of a small wind turbine just as a large wind turbine, which is small. Of course, that's true, but their characteristics are much different. According to the position of the rotor, we distinguish between horizontal and vertical axis wind turbine. Most of the wind turbines, 16 wind turbines, are horizontal axis. For the large scale, all of them are horizontal axis. And in the small scale, we can find some vertical axis wind turbine with different designs. The number of blades, the most typical number of blades is 3. For all large scale is 3, and for a small scale, it's the most typical, but we can find also another numbers from 1 to up to 5, 6, and then the multiple blade American windmill we saw before. According to the tip speed ratio, the tip speed ratio is the relationship, it's a dimensional parameter, which is a relationship between the linear speed at the tip of the blade into the wind speed. So it's as I said, a dimensional parameter which defines if a wind turbine is fast or slow. And not to get tricked by the word fast and slow, because, for example, if we see large scale wind turbines nowadays, they rotate at a very low rotational speed. but they are not. They are quite fast because even the rotational speed is low, the radius of the wind of the blade is quite large. So the multiplication of a low rotational speed by a high radius produces a high tip speed ratio. And in this graph, which is quite classical also, we can see the Betz limit we saw before, which is the theoretical maximum efficiency of the captation extraction of the wind turbine. But here we can also see the Glaubert's limit, which imposes physical limits according to the design of the wind turbine. And we can understand through this diagram also why the three blades, oh, sorry, it's in Spanish, but the three blades wind turbine is the most common because it's the most efficient. According to the control, we could find, because nowadays they are not very common, the stall regulation rotors. The stall regulation is an aerodynamic, a passive aerodynamic regulation, just because of the functioning of the rotor of the blades. When the specified wind speed is reached, the turbulence increases and the efficiency of the rotor decreases, and there is a natural and passive natural regulation in the rotor. As is the problem of this regulation, the advantage is that it's very simple, but the problem is that it's difficult to regulate, to control. Nowadays, all of the large wind turbines use this active regulation on the regulation zone, and they regulate changing the pitch with a pitch control. They vary the angle of attack, as we saw before. Varying the angle of attack, the control can maintain a constant output production. Another classification is according to the control system, where the working principle is depicted here. Not all the generators are permanent magnet, but most of them are, well, the trend is that the synchronous generator is being more and more. In the past, in the near past, and maybe even nowadays, there are still some models that use asynchronous induction generators, but it's called the doubly fed induction generators. And the last classification I will mention is the one that appears in this standard of the IEC, that defines some classes for the wind turbine. I mean, the same model of the wind turbine may have different classes according to the site. This is an interesting classification because it's site dependent. It depends on the site where the wind turbine is going to be installed, according mainly to the wind resource and also to the turbulence intensity of the site. Okay, so we will move to the wind resource block, and here are some aspects we will address from the wind resource, starting from the sources to look for data. These sources for data are mainly for either for academic studies or for small wind turbines, because usually large wind turbines don't look so much for external sources. They have their own measuring campaigns. Here, I just I'm sharing two data sources which are global, so that they can be used everywhere. When a measure campaign is carried out, then here are the main characteristics of the measurements. Of course, wind speed is critical. If we are able and we get enough money, we also should include wind direction, temperature, and pressure. And here we have the instrumentations that are needed for the wind speed measurement with the anemometer, which nowadays we have different options. The CAPS anemometer is the cheaper of these three ones, and the sonic and LiDAR are, well, nowadays are quite common in large wind turbines. The sampling rate is different for each parameter according to the speed of vibration of this particular physical effect we are measuring. For example, for the wind speed and wind direction, we usually will measure 1 sample per second and then produce average every 10 minutes usually. For the pressure and temperature, we don't need such a high sampling rate. Ideally, the campaign duration would be 1 year, if possible, and we have to take into account the sensor calibration and position. Once we have the measurements, or perhaps we could say, what's the information we need? Of course, we need the average wind speed. We can have the hourly average through 1 day, the hourly average through 1 month, month by month on a monthly basis, and the average wind speed on a yearly basis. The wind rose, it depends. If the wind rose is critical if we are going to make an obstacle study. If we are not, then we don't need the wind rose. If we are just if we want to calculate only the energy production, with the average wind speed is enough. But if we want to take into account the effect of the obstacles, then we will need the wind rose. The wind shear is the variation of the wind speed with the height, not to confuse with the variations of the wind speed of the energy production with the altitude, which, as you remember, it was in the previous equation at the air density. Here, the shear is for a particular site with a fixed altitude. Then, depending on how much we move from the ground, the wind speed will increase because of the ground is like a brake for the wind. And remember the effect of the altitude also. So we have different options. We don't have much time, so I will go a bit quicker on this part. This is more for the calculations, depending on the type of data we have. If we have measured data, then just the calculation of the energy is as simple as use for each hour, for example, this the wind speed for that hour and enter into a power curve and see how much energy I'm getting that hour and make a summation for the whole year. But as I said, it's not always the situation, and maybe we don't have this measured data. And maybe what we have is the probability density distribution description. This probability density for the wind resource characterization, the one that fits better is the Weibull distribution, the Weibull function, which is this one. And you can see that is defined by only 2 parameters, the shape and the scale parameters. So the great advantage of using the description of the probability density function is that only with 2 parameters, the shape and the scale parameters, we have an estimation of the wind resource on a particular site. This is particularly practical, for example, in global wind maps, because of course, in a global wind map, we cannot work with measured data directly. So maybe we will need to perform a temporal extrapolation just to know if the year we are using as a reference is representative of the wind resource in that site, and spatial extrapolation. Here is described the model used in WASP. WASP is a very commonly used tool to evaluate the wind resource for wind farm planning. And this model proposes to eliminate the influence of the site in which the wind speed has been measured, eliminating the influence of the orography, the roughness, and the obstacles, obtaining what is called geostrophic wind, which is the theoretical wind, which is at the upper part of the atmosphere, and this wind is supposed to be the same everywhere, I mean, within a particular region. And then once we know the geostrophic wind, we can particularize this geostrophic wind, which is common to each one of these pixels. We can calculate which would be the wind at each one of the pixels, including for each pixel the influence of the orography, the roughness, and the obstacles for that particular pixel. This is how, with only one measuring point, we get the wind estimation for a whole area, extrapolating spatially. And the calculation, how do we perform the mathematical calculation of the wind turbine output production? We need a characterization of the wind resource, which might be through the wave function, which is, in this case, this is taken from an Excel file. This is, for example, the wave function for this for some particular shape and scale parameters. We need a characterization of the power curve of the wind turbine. And once we have a characterization of the site, of the wind resource at the site, and a characterization of the wind turbine we are using, we can calculate the energy. This is really a numerical integration, which is done in bin by bin. Each bin is this interval we are dividing the wind speed range, in this case from 1 to 20 meters per second. We made a multiplication bin by bin, and then we make a summation of all the results. And this figure, this number we obtain down here, represents the average power that this wind turbine produces in this particular site. So this is a result, of course, the average power is a result itself, but it's not a result that is commonly used. The most commonly used results are the ones that are here, the annual energy output, which is the total energy that the wind turbine produces in this site, and is calculated multiplying the average power, which has been calculated here, by the number of hours per year. Another common parameter is the equivalent hours, which is calculated dividing the annual energy output into the nominal power of the wind turbine. It's equivalent to the number of hours that this wind turbine would be working at nominal power to produce the same energy. And finally, the capacity factor we saw before, which is a relationship between the average power into the nominal power of the wind turbine. Okay, well, this is just to show how to calculate it. Usually we use either self-made Excel sheet, for example, or some of the existing tools that are available for this calculation. Okay, so we enter into the last block with not much time, but I will try to cover it all briefly. We will start with the economy. In this graph, we can see how with the deployment of the wind turbine during these years, the cost of the generating cost of the wind generation, we're talking about the large scale, has decreased accordingly to the increase in the installed wind power. This is what is usually called economy of scale, and this is supposed to, of course, this has a limit, but this is supposed to still have some range to vary. I mean, it is expected that the limit is even lower for the generating cost. Nowadays, which are the most common remuneration modalities? I mean, how are the wind farms that are being installed nowadays paid? These are the main modalities. Maybe they are not all, but they are the most important ones. The auctions are very common here in Europe, or also in America. The power purchase agreement are more common in America, but also here in Europe, they are starting to increase their presence. The feed-in tariff have been very, very common here in Europe and in America, but nowadays they are most common in China. And the tradable green certificates and the tax incentives are economical incentives to the investment in general in renewable energies. During the last year, 2020, here in this graph, we can see the percentage of each modality on onshore applications. I mean, on the ground. We can see how the feed-in tariff is the most common modality in China, as China is the main market, has been the main market during this year. That's why it has such a strong presence. The US is mainly using the tax credits, and the auctions are being used mainly in Europe and South America. The PPAs are not defined. Maybe I think they will be here in other, but as I said, their use is becoming more and more popular during these months. This is the evolution in the increase of wind power during the last few years, and we can see that it was more or less stable, but during the last year, it has increased quite a lot, more than 50%. So the trend is that this increase will this increase in the installed power will be maintained for the future years in order to meet all the scenarios that were described in the previous session. This is the new wind power capacity in 2020. Most of the new installed wind power capacity has been installed in the area Pacific region, followed by Europe, North America, and Latin America. For Africa and Middle East, we find here 1%. Of course, 1% of 93 gigawatts is nearly 1 gigawatt, which is not so bad. And these are the main markets. China is the first one, followed by the US. This has been during the last year, 2020. In overall, if we take an overall view to the whole installed power, China is still the leader, but and also followed by the US. But we can see that the third one is Germany, followed by India, and here Spain, France, Brazil. This is for onshore application. The offshore market is, even though China is also present, but is mainly based in Europe until now. United Kingdom is the leader for the offshore market, followed by in Europe by Germany, Netherlands, Belgium, and the rest of the world. And I brought this slide to see which are the expectations in Africa. They are only classified, they only distinguish between South Africa and the rest of Africa and Middle East, because South Africa in Africa is the country where in general renewable energies are more deployed. But the expectations for the following 5 years, we can see that, of course, this general growth that is expected everywhere is also expected in this region. Mentioning some of the main manufacturers in the world, the main manufacturer is the Danish Vestas, the manufacturer from Denmark. Then GE Renewable Energy, which is from the US, Goldwind, Chinese, Envision, also Chinese or half Chinese, and Siemens Gamesa. Gamesa was a Spanish manufacturer, but now they merged with Siemens, and well, we could say that they are German, Spanish, maybe more German than Spanish nowadays. And finally, the last point, which are the technology challenges, I will just mention very briefly. As the size of the wind turbines is increasing so much, and also the size of the wind farms, and both onshore and offshore, the influence between wind turbines and between wind farms is bringing new challenges that were not shown before because of this very large size. Precisely this, we have to think that the wind turbines that are being proposed nowadays use blades, each one larger or around 100 meters, which is very, very large blade. So there is a challenge in materials, in efficiency, in loads in the blades. And you can see a comparison between blade in the 1980s and the current generation blade, which are much more thin, but of course much more complex also. And finally, the challenges that the integration, this very large integration in the electrical grid bring. This is not only for the wind generation, but also for all renewables. But of course, it influences also the wind generation. Okay, and here were, well, the three references. Really, the two first ones have been used in this presentation for the preparation of the respective chapters. And the third one is just for those of you who would like to take a look at the use of small wind turbines for rural electrification. Here you have a reference you can use if you want. Okay, thank you very much for your attention, and I sorry because I think I took more time than expected, but I hope we have some time for this discussion.
Thank you very much for your interesting and intervention. Not only interesting, but you were able to explain difficult things in a relatively easy and clear way. So we have the time is over, of course, but we have room for a short question. Go ahead, please. Yes. Any question? Yes. So if there is no questions, we stop here, and thank you very much, and thank you to all the attendants for your attention. Thank you very much, Luis, for your intervention. So see you tomorrow at 10 o'clock, and have a good day. Bye-bye.
Thank you. Bye-bye.
Bye.
Thank you.
Bye-bye.
Thank you.
Thank you. Bye.
Bye. Thank you.
Thank you all.
Thank you very much.
Hola, buenas.
Hola, Alba.
Hola, buenas. Hola.
Hola, ¿qué tal?
Bien, estaba yo aquí entre reunión y reunión pendiente y he visto que, bueno, todo ha ido muy bien, ¿no?
Sí,
Yo sin
muy bien.
querer creo que silencié por error un momento a Luis porque estaba trasteando, porque estaba subiendo los materiales al curso y estaba viendo las opciones porque me parece que no permite. Si le pudieses preguntar a Conrad una duda que tengo y es si los materiales se pueden. Bueno, hay dos cosas. La primera, has puesto una carpeta de materiales de clase y no me deja cambiar el nombre. Quizás tú, como lo has creado tú, a lo mejor a ti sí que te deja hacerlo para que lo pongas en inglés, para que pongas Slides and
Sí,
Documentation o algo así, ¿sabes? Para.
lo puedo mirar porque creo que eso nos lo creó Conra el día que hicimos como
Ah,
la pequeña formación, pero
sí.
ahora lo miro.
Pues entonces, si vas a hablar con él, dos cosas. Lo primero, si le puede cambiar el nombre para que lo ponga en inglés, hay algo de documentation o algo así, o slides o and materials o algo así. Y luego la segunda es, cuando he subido los materiales, que ya lo he organizado por ponente y por número, por día, para que se vea por orden, vamos. Dice que les permite consultarlo, pero no descargarlo. En principio no hay ningún problema en que lo puedan descargar. Si se puede desbloquear eso, pues fenomenal.